This thing is called as a normalizing factor in the front. So this normalization, which will be seen in other forms, in other filters also. Okay, normalization serves two purposes. Okay, one, if you have, so in your image, if you have some area where the average, where the intensity is constant, okay, suppose the same pixel values are there, then after filtering also they will stay the same. Okay. This normalizing ensures that for an average value of area, the average value of an area of constant intensity remains the same. Okay. So not much change. If in the original image there is not much change happening in this part, then in the filtered image also it will look like that. Okay. So that is one of the advantages, or one of the reasons why normalizing should be done. The other one is that no bias is introduced during filtering. Okay. So this is important. We will see one quick example of what happens if bias is introduced. But essentially what this means is that in the original image and in the filtered image, the sum of pixels remains the same. Okay. You are averaging this at every point. So the sum of pixels in all does not change in the original and filtered images. Okay. So these two things are very desirable in a lot of filters. Okay. So in various ways, this normalizing will be introduced for the other filters also. So another point to note is that because of the nature of a box filter, if you view it as a matrix, it has rank 1, which means it's a separable filter. I hope you remember what is a separable filter or a separable kernel. Separable kernel or separable filter means some filter of rank 1, so that it can be written as a column times a row. Okay, and then so convoluting with this matrix is more expensive than convoluting first with this and then with this. Okay, so if a kernel is separable, it is advantageous in terms of computations. Any rank 1 filter will be separable simply because you can write any rank 1 matrix as a column times a row. And in practice, what happens is, although this is easy to design, it is useful for quick experimentations. Okay, but it will not give you sort of uniform smoothing effect. Okay, so we will see one or two examples now. So because of this, it favors blurring in perpendicular directions. Okay, I'll show you what this means. So the blurring is not smooth. Okay. And the second thing is that for image enhancement or for artistic purposes, usually blurring is, one wants the blurring effect to be like that of a defocused lens. Okay, this is what is desired. But blurring that comes from the box filter does not replicate that effect. So these are the cons of box filters, but of course they are very useful for quick experimentation. Is blurring going to help you at all? If you want to just quickly check it, use a box filter. Okay. So here is a code demonstrate what the box filter does. Okay, so here I have some image with these two squares in it. Okay, so if I use, let's say, this box filter. Okay, so I'm going to use, so kernel 1 is just a 3x3 filter here. Okay, so this is a 3x3 filter. It's a box filter. I have this normalizing constant 1/9 here. Okay. So what does this do? So if you look at the image as it is, it won't really show much difference. First of all, it has done blurring. Okay, this has become this. But if you want to see closer or in more detail what it's actually doing, you should look at the zoomed image. So this is what it does. Okay, so this is 3x3. So this 3x3 is actually giving rise to this 1, 2, 3 levels. Okay. On the other hand, instead of 3x3, if I had done 5x5, okay, I think that is one of my listed kernels there. Yeah. So instead of 3x3, if I do 5x5, so you can see what happens here, right? This is the difference between the kernel, what the kernel sizes do to the image. Okay, so this is box filter. What happens if you don't put that averaging or you don't do the normalization? So suppose I remove this 25. Okay, and just use this. Okay, so no 1 over 25 as the normalizing factor is being used. Then simply you will see that the intensities change. There is a complete change in the intensities, right? So this is what will happen if you don't use the normalizing factor. So that was just some quick experimentation. All right. Moving on. The most used filter. Okay, this is the Gaussian filter. This is the most commonly or most favored filter. Uh, this takes care of exactly this problem that box filters have, which is that they cannot replicate this soft blurring effect. Okay? So the soft effect cannot be done with box filters. On the other hand, with the Gaussian filter, you can get this soft effect. Okay, so here is X, Y, Z. This is roughly what a Gaussian will look like, right? I'm sure you must have seen this function many times in your statistics courses. Now, if you look at it from the top, okay, then it's going to appear like this. If I draw sort of the level curves, okay, the top here, okay, so basically this is circular, right? This is this kind of function, okay, where the Gaussian is defined like this, okay. This is going to be circular about the origin. Okay, so the level curves are going to be these circles, correct? Now, if you design a filter with this in mind, okay, so you have some quantities here. Okay, now filter, for obvious reason, you want it to be an array, so it's going to be square. Okay, so you are going to require. So if you decide to put a filter with these values like this, okay, which means you put this value in this place, okay, this value in this place. Similarly, this middle box lies on some circle. You put that value here and so on. Okay. These values you put in these corner boxes. Okay. So here is an example, something like this. Okay. Right in the middle here, which is going to be sort of the top of this Gaussian, okay, will be higher value of Z. So that's 41. Okay. These are sort of the numbers that depict the height of the circle that they are on. Okay, so these are all circles, right? What I'm saying, does that make sense? These are all circles, right? Level curves. And the Z value is the height. Okay, so this 41 sort of saying that the height is 41 here. This next one, these four lie on a circle. Okay, so that's 26. These will lie on a next circle and so on. Okay, so if you try to replicate the idea of a Gaussian in terms of a kernel, this is what the kernel will look like. Obviously, for the reasons mentioned earlier, you would like to put some kind of normalizing factor outside of it. So this is the idea of the Gaussian kernel, and the definition is this. So it is defined like this. Usually this k is taken to be 1 over 2 pi sigma square, or or maybe the square root of it, or 1 over root of 2 pi sigma square, one of these things. Or as I took it here, it could also be simply the sum of the pixels. Any something like this. K is called the normalizing factor. Okay. If you write it in polar coordinates, the same function looks like this. And this tells us that GR is circularly symmetric. Okay. Or the picture also tells you that. So the point is, it has the same values along a circle of radius r. So it has no directional bias. Okay. On the other hand, here, when we had these box filters, okay, you would get something in the x direction and something in the y direction, right? Even in those images that I showed you earlier, okay, you had this blurring wasn't sort of smooth or round. Okay, this was in perpendicular directions. Correct? In something happening in the x direction here, something happening in the y direction here. Okay. So this kind of thing, that this favors direction, it does not happen with Gaussian blurring, because it is circular. It goes around this circle, which has the same values. Moreover, to make things even more nice, G is also separable. Okay. This function can be written as the product of these two functions, which are both one-dimensional kernels. So this is a separable, circularly symmetric kernel. This is in fact the only separable and circularly symmetric kernel. Okay. So this is the reason why this is the most commonly used filter. So here I have written just one example of a 5 by 5 Gaussian kernel, okay, with sigma being 1, standard deviation 1. Yes, the effect of convolving with G is a smoothing that weighs pixels at the center. So obviously here you can see these are going to be the weights that you assign to the pixels, right? You are going to convolve with this, which means this 41 gets multiplied to the center pixel of whatever your window is. So the highest weight is given to the center pixel, and lesser weights are given to the pixels which are farther from the center. Okay. So that is the main property of one of the main properties of this Gaussian. Another piece of terminology here is that this is what is called, so something that is has no directional bias is called an isotropic filter. Okay. So a filter which has the same effect in all directions. So the Gaussian filter is an example of an isotropic filter. Sometimes the situation is that you don't want an isotropic filter. You want to favor uh, blurring in some direction. Okay, you want to give some direction. Then in that case, what is done is selective smoothing. Okay, so when smoothing in certain directions is required, okay, and because it is not isotropic, it is called anisotropic. Okay, such filters are called anisotropic filters. So there are various types of selective smoothing, and one of them is directional smoothing. So these are, I have just listed the steps that one does, but the idea is that so suppose you want to fix some direction for smoothing. Suppose you decide you want to go in directional smoothing. You first calculate the average in all directions. Okay, and then suppose you want to go towards the minimum direction. Okay, then you replace this center pixel by a weighted average. So suppose the minimum direction comes out to be this direction. Okay. Then you replace this by an average of these two pixels. If the kernel is bigger, then you will take the weighted average of these 3 pixels and replace the value of the center pixel with that. So this is how this directional smoothing kernel works. Okay. So spatial average simply means average of the pixel values in every direction. So suppose this is the center pixel. You just, so if you take 8 by 8 neighborhoods, so you are calculating what spatial average in all these directions, okay, like this. And then you take the minimum and you decide to replace the value of the center pixel with the average of these. Whatever average you want, a general, not just a non-weighted average, you can do that, or a weighted average. So something like this is called directional smoothing. Then there is also conservative smoothing, where you replace the center pixel value by the minimum of the center and the max value in its 8 neighborhood, okay, or the maximum of the center and the minimum value. And if neither of these conditions happen, then you retain it as it is. Okay, so this is conservative because it does not do something. So for example, directional smoothing makes a lot of change, whereas conservative smoothing will not make so much of a change. Well, there are many more also actually. So I have just written 2 examples here. So here the kernel is not sort of fixed. Okay, here it is depending, every time you move, you have given a rule for the kernel, that's all. On the other hand, here you have actually set the kernel with these values, with these weights in it. All right. So this median filter in the order statistic filter simply means filters that depend on the statistics of the image. So statistics means you could have mean, median, max, min, okay, all those kind of things. So the median filter, it simply replaces the value of the center pixel by the median of the intensity values in a chosen neighborhood. Okay, the neighborhood could be a 4 neighborhood, 8 neighborhood, or some other shape neighborhood like this. Okay, so this shape neighborhoods are also various shapes can be taken. Okay, so the shape is decided, and then the median of those values is taken, and that replaces the value of the center pixel. So what the speciality of the median filter? So among all these filters, the median filter is the most commonly used one. Okay, and it is most commonly used for removal of noise. Okay, a particular kind of noise which is called as, so there are types of noises which I will discuss a bit later, but there is this one noise called impulse noise. So impulse noise, colloquially also known as salt and pepper noise, is noise that occurs only in dots somewhere. Okay, it's not continuous, it's also not throughout, or how do I say, it's not like these very closely placed. Okay, so not noise like this, but noise that sort of appears as discrete dots. Okay, so this kind of noise is very effectively removed by the median filter. Okay, for the following reason. So suppose you have, suppose these are the pixel values in the original image. Okay, then what the median filter does is, this center pixel is going to be replaced by the median of all the values with the center value included. Okay, so you take median of these 9 values and replace this 15 by that. So what happens is, if it turns out that this is where the impulse noise is, okay, so there is this exactly one pixel which is creating the noise, okay, which means it is definitely different from the other neighbors, okay, which are more like each other. The impulse noise, the idea is that there is just this one pixel which is causing the problem, and the neighborhood is sort of uniform. Okay, so all of these will chip in to remove this noise. Okay, so this pixel will become more like the rest of them. That's what the median does, because the median is going to be more dependent on what these neighborhood values are. Okay, so this is the way the noise will vanish. Okay, so that is why the median filter is very useful for this kind of impulse noise. So among the order statistic ones, I have only discussed the median filters. The other ones are also used from time to time. So those you can see whenever you need them. Yeah, so the main kind of or family of filters that I want to discuss now is what is called as the gradient and Laplacian filters. So gradient filters, which mean, so gradient simply means taking derivative, right? So and Laplacian means you take the second derivative. Okay, so these derivatives help us find out the edges in an image. Okay, because gradient in images refers to the difference in pixel intensities. Okay, so these are very useful in edge detection. So let us just sort of try to understand just the heuristics of how this works. So what this is it is the, so you remember this line scan of an image. So you have an image, you take a horizontal line across it, and then you start reading the intensities from left to right. Okay, so that is called as a scan line, horizontal scan line of an image. So what they have done here is they have just plotted those intensities like this. Okay. So x is the distance from the left border, if you like. Okay, and along the y-axis are the intensities. Okay. So right in the beginning of that horizontal scan line, the intensity is 6. Then for the next pixel it is 6, next pixel is 6, next pixel is 6, and then it's going down. Okay. So that is how they have just plotted all these intensities along a horizontal scan line. Okay. Now when intensities are plotted in this way, either you could observe something like this, where there is no change in intensity, so we call it constant intensity, or something like this, where the intensity is changing as continuously as possible. Okay, so this is a discrete setting. Okay, but still 6, 5, 4, 3, 2, 1 is as continuous as possible. Okay, so if it changes like this, then such a feature is called a ramp. Okay, again here you see constant intensity. Now from here, if you go from this pixel to the next, what is happening is that the intensity suddenly jumps up. Okay, it's not smooth like this, it is just jumping up. So such a feature will be called a step up, or it could be step down, and then again constant. Okay. So this is simply the intensity profile along some horizontal line in some image. Okay. So here what they have calculated is derivatives. So now for a discrete function, how do you calculate the derivatives? This is called the method of finite differences. So finite differences simply means that forget the corner points. Okay, we are not going to calculate the derivative at the corner points. So now let's look at this one. Okay, you want to calculate the derivative at this point. Okay, so the derivative at this point at any point x is fx plus 1 minus fx. Okay, you take these differences. Okay, so this next 6 fx plus 1 minus 6, that gives you this derivative is 0. The first derivative at this point is 0. The derivative at this point, first derivative, is this 6 fx plus 1 minus fx, so that's 0. The derivative at this point is 5 minus 6, that's minus 1. So this is 5 minus 6, then 4 minus 1, 3 minus 2, 2 minus 1, 1 minus 2. So all these are minus 1. Okay. Then you have 1 minus 1, that's 0. So here the derivative is 0 again, and so on. This is how the first derivatives are being calculated. Okay. How are the second derivatives calculated? So in this finite differences, there is a formula for the second derivative also. Okay, so this is in 2 dimension. I want to show you the 1-dimensional form here. This is the finite difference in 1 dimension, right? Fx plus 1 plus fx minus 1 minus twice fx. This is the second order derivative in the theory of finite differences. So that is exactly that is done here. Okay, so you want to calculate the second derivative here. That's going to be 6 plus 6 minus twice this, which is 0. 6 plus 6 minus twice this, so 0. 5 plus 6, 11 minus twice 6, so that's minus 1. Okay. So this is how these second derivatives are calculated. Okay, and just as you do for continuous functions, you can make conclusions about how the intensity is varying, how fast or slow, using these first and second derivatives. Okay, so now here what they have plotted with the dots, they have plotted the first derivative. Okay, and with the squares, they have plotted the second derivative. Okay, so now at this point, for example, the first derivative as well as the second derivative is 0. So you have a dot as well as a square here. Okay, whereas here these are only dots because these are first derivatives at these points and the second derivatives are here. Okay. So this is just plotting the first and second derivatives for this intensity scan line. Okay, so now in this kind of image, well, of course, you expect something to happen here, right? Yeah, because there is a quick jump here. So this jump in terms of the first and second derivatives, well, in terms of the first derivative, it corresponds to this being 0, right? In terms of the second derivative, what happens is that so the second derivative at the earlier point was up here, and at the next point is down here. So if you join these two second derivatives, then you get a line that passes the horizontal axis, and that's called the zero crossing. Okay, so these zero crossings, if there are more of these, okay, wherever you get this zero crossing, it corresponds to a jump in intensity. Okay, not smooth like this, but a quick jump. Okay, and one can expect that that jump is happening. So if this is happening along the horizontal scan line in an image, okay, then one can expect that that jump is happening because the intensity is changing as you go from one pixel to the other. And this intensity change could correspond to the presence of some feature like an edge. Okay, So these zero crossings are exactly what one needs to find in order to sort of detect the edges or contours uh, in an image. Okay. So this is the idea. This is the underlying idea of all those gradient methods that are used. So this is the idea of taking the gradients. Now this can be done using various kernels. So this is what we will look at now. So finite differences is the key word here. Okay. You're dealing with discrete values, discrete functions. So you should be taking finite differences. Okay, so moving on. Yeah, so here are the formulae for the two. And the Laplacian is simply you take the sum of these in the two directions. The point to note is that the derivative and the second derivative both are linear operators. And so first of all, because they are linear, okay, you can express them as convoluting with a kernel. Okay. So this convolution with a kernel you can do for any linear operator. Right? So that is exactly why we can express the gradient and the Laplacian as convoluting with some kernel. Okay. And the corresponding kernel will be isotropic, which means independent of direction. Okay. So let's look at some. Yeah, so here what I've done is just written the simplification of this formula in two dimension. Okay, so if you have dabba 2f xy, then so if you write out all the terms for the second order derivative and simplify, this is what you will get. So I've just written that down once. But then you can see what should be the kernel that corresponds to this. If you write this down, okay, so then the kernel that corresponds to this formula should be, well, you are definitely looking at the center pixel xy. Okay. And then you're looking at x plus 1y, x minus 1y, xy plus 1, and xy minus 1. So you're interested in the 4 neighborhood of this center pixel. Right? So here is your center pixel xy and these 4. Okay. And what coefficients are they coming with? So each of these 4 neighbors are coming with coefficient 1. And this one is coming with coefficient minus 4. So and these are not playing a role. Okay. So this is exactly the kernel that corresponds to taking a Laplacian. One can also take another. So I think I have written it later. Yeah, one can take. So this kernel is here. You can also take the negative with a minus sign outside. Okay. I'm not saying you can take, but some people do take with a C minus 1, but the operation is supposed to be the same. Okay. The only interesting thing is you can also take other kernels which try to incorporate the diagonal elements. Okay. So now what you will do is you will also add these 4 elements. But if you try to substitute that in the formula for the Laplacian, you will have to make adjustments with the center pixel, which will amount to taking minus 8 here. So you can check that some addition subtraction needs to be done. Okay. Or the negative of this, which is this. So the Laplacian is usually one of these 4 kernels. Okay. If you don't care about the diagonal elements, then you can use either this or this. If you want to incorporate the diagonal elements, you can use the third or fourth. So that is what taking the Laplacian corresponds to. So there are a few more things about the Laplacian and the gradient, but I will come back to it. Okay, here, so one of the things that you can do with the Gaussian or even with the Laplacian is create a mask. Okay, so here in this case, in this unsharp masking and high boost filtering, this mask is a blurred image of the original. Okay, so you take the original, you blur it, and then you subtract it from the original image. Okay, so that is called a mask. But this mask can be created in various other ways also. Anyway, if you create it like this, the process is called unsharp masking. And then in the end, you add the mask to the original. So this you can see what it does. So something like this. Okay, so this is the original image. This is the blurred image and this is the subtracted image. Okay, so this is the mask. Now this mask you add to the original image. Okay. So this is what unsharp masking does, is it sort of makes the image clearer. Okay, so this was the original image and this is the result of unsharp masking. Okay. So this is a very old idea actually. It's been used in the printing business for a long time. Okay. You blur it first, then you subtract it from the original and then add the subtracted result to the original. That sort of makes the image sharper. The same thing you can do with a, so there is this factor of k here. So if k is equal to 1, okay, we are simply adding this image to the original, then it is called unsharp masking. If k is greater than 1, you put some number greater than 1 here, which means you weigh the mask more than the image. Then that process is called high boost filtering. It will produce something like this. If k is taken to be less than 1, then you are sort of reducing the weightage given to the mask and it doesn't produce any nice results. Okay, so k less than 1 is never taken. Either you take k to be 1 or k to be greater than 1. So that is this process of unsharp masking. Okay, so but as I said, I want to come back to gradient filters. Okay, so here in the book there were some images here. Yeah. So this is a blurred image of the moon. Okay? And this is what the Laplacian looks like. Okay? So the Laplacian, if you remember, is convolving with that kernel 0, 1, 0, 1, minus 4, 1, 0, 1, 0. So convolving this image with that kernel will give something like this. So you can imagine why this might be happening, because if you look at any one pixel, you're weighing the center pixel with a minus 4. Okay, and you're replacing the center pixel with the sum of the 4 neighborhood and minus 4 of the center. Okay, so the image is definitely going to go darker except at the edges, because at the edges, see, these neighborhood pixels are also going to play a role. So except at edges, you will see, or a better way was simply because of this behavior, okay, where you get the 0 crossing at the edges. That's a simpler explanation, but anyway, you can look at it either way. So this is the Laplacian, okay, and then this image sharpening is done, okay, by adding the image to the original. So by adding the Laplacian to the original image with a factor c. Okay. So this factor c is what I showed earlier. Okay. It could be 1 if you are using this kernel, which is, yeah, if you're using this, you will use c equals 1. If you use this, on the other hand, you will use c equals minus 1. So the Laplacian is most commonly used like this. So you take the original image, take its Laplacian and add that Laplacian back to the image. The result is a sharpened image. So this is the image sharpening with c equal to minus 1. And this is the image sharpening with the kernel that has diagonal elements also, which is taking diagonal elements also in consideration. So you can clearly see the difference between the original image, okay, and these two images on the bottom row. Okay, so adding the Laplacian to an image sharpens the image. And I mean, one common sense way of thinking about that is, well, the Laplacian is just all the edges and sharp contours that are appearing in the image. You are adding them back to the image, okay, so they will be more enhanced. So essentially, that is what is happening. All right. So coming back here. Now these gradients can be used in many ways to form filters. So, well, we know what the definition of the gradient is. Okay, this first derivative, second derivative, where derivatives for images are going to be calculated using finite differences. The magnitude of the derivative is just calculated like this. Yeah, there is one kind of plot which is called the gradient image. It simply plots these magnitudes at the locations of the pixels. There might be an example in the book that shows that. But anyway, so there are a number of filters that can be formed using gradients. Okay, so some examples. This is the most commonly used one. Okay, you might have already seen this name, Sobel operator, the most commonly used. Then there are other Roberts cross gradient operator, Prewitt operator, and this gradient filters are also used in this very commonly used edge detection algorithm called the canny edge detection. So I will not talk about the canny edge detection right now. There are many other steps that go into this algorithm. But this Sobel operator and the others are very not difficult to explain. So the Sobel operator is simply given by these kernels. So what this kernel does is it calculates the gradients in the x direction. Okay, so you can imagine what happens if you are applying this to some part of the image. Okay, so suppose this is, I will do this in some other color. So suppose this is part of the original image. So let us call this A, B, C, D, E, F, G, H, I. Yeah, not good names. Let's just call this X1, X2, X3, X4, X5, X6, X7, X8, X9. So you can see that the Sobel operator just comes from the definition of the gradient. Oh, I have been really sorry, I've been quite stupid. There is a natural numbering that you have with this. And I should just use that. So this is your X comma Y. This is your X minus 1Y, X plus 1 comma Y. Excuse me. X comma Y plus 1, X comma Y minus 1. Okay, and the diagonal elements. Okay, but yeah, we'll write them as we need them. So this is X minus 1, Y minus 1, for example. Okay, so then if you want to calculate the gradients, what does this do? Convolving with this do. So this looks at this minus this, right? So this is what this is X plus 1, Y minus 1. Okay. So if what this is going to do is these are all F values, right? F of this, F of this, F of this, and so on. So this convolution is going to take F X plus 1, Y minus 1 minus F X minus 1, Y minus 1. Okay. So your Y minus 1 is fixed and you're looking at the derivative with respect to X. Correct? This minus this. Similarly, you're looking at this minus this and then this spot minus this spot. So you're looking at derivatives with respect to X. So this is Gx. Okay. But now here what has been done is here they have added a 2. Okay. So these are being weighted. Okay. So instead of just taking this minus this and this minus this as well as this minus this, you're taking twice of this and twice of this. Okay. So when you take the sum of all those, you're sort of calculating some kind of average of these minus a weighted average of these. So a weighted average of these pixels minus weighted average of these pixels and replacing the center pixel by those values. Okay. So you're replacing the center pixel by those derivatives. Okay. And so on. So this is happening in the X direction. So this is Gx and this is Gy because the same thing will happen in the Y direction. You could also have, you could have taken this as non-weighted. Okay, you could also have taken 1, 1, 1, and that actually is this Pruitt operator, where sorry, I have got the directions wrong here. So in the Pruitt operator, you are also doing the same idea, except that now you are not taking weighted sums. Minus, minus, and this should be with the in these ladder 0, 0. This Roberts cross operator, on the other hand, so the top left corner is placed on the center pixel. Okay, so then if this is, so now I will just use ABCD. So if this is the image and this is the pixel on which GX is placed, okay, then what this is doing is it's taking D minus A. Okay, so the change in this direction, if you like, okay, and this is doing C minus B. So change in this direction. Okay, so this is why it's called the cross operator. Okay, so convolving with this will take the change in one direction, and then you convolve with GY will be corresponding to change in the other direction. So this is the gradient operator. So you place. Oh, by the way, I didn't say, but you should be convolving with both. Okay, so the function, the image is convolved with GX and with GY. Okay, and that result is placed at the center pixel. So this convolution is done with.
Madam, will the sequence matter?
What do you think? You remember the properties of convolution? So convolution is commutative. Okay, so if you are doing actual convolution, not correlation, then it doesn't matter. Okay.
Got it.
But so as I said, one has to be careful when one writes programs. Okay, because no, I'm not saying that you have to be careful when you write programs, but people who write these codes, original codes, okay, have to be careful because as far as I know, what is used in CNNs is correlation. Okay, correlation with a flipped kernel. That is what they use, and that stands for convolution. In fact, sometimes they don't even use the flipped kernel; they use only correlation. That is okay if your kernel is symmetric. Okay, if your kernel is symmetric, it doesn't matter. Convolution and correlation are the same. But if the kernel is not symmetric and you want to do mathematically convolution, then the operation using correlation, then the operation is correlation with a flipped kernel. So you just have to keep this in mind. But if you are doing actual mathematical convolution, the operation, the order does not matter because it's a commutative operation. Okay. You remember this thing when we talked about convolutions and correlations? Is that idea clear or is it not clear?
It's clear.
Yeah, you just have to remember correlation equals convolution with a flipped kernel plus flipped kernel. Remember, correlation is the one where you keep the order of these and the image pixels the same. That is correlation. So it is easier to implement and easier to think about. Convolution is where you take this 180-degree flip and then you do the correlation. So whatever operation, sum of products operation with the underlying image. So convolution is a little difficult to imagine, while correlation is very easy to imagine. But mathematically, convolution has better properties than correlation. Okay. And finally, correlation is nothing but convolution, or you could also say the other way if that suits you better, that convolution is nothing but correlation with a flipped kernel. So either way is the same thing. Okay. And finally, the point to remember is that most programs implement correlation, even if uh, it reads as convolutional network or whatever. So whenever the word convolution is used to represent both operations, convolution as well as correlation. And usually things are taken care of by flipping the kernel somewhere in the process. Okay. So that is what you need to remember. And so in theory, you will see everywhere that the commutativity and associativity are used freely, because usually one is talking about actual mathematical convolution. And one expects that while writing the program, people will take care if they're doing correlation. Okay. I hope I didn't confuse you more. I just wanted to sort of make it clear that you can freely use commutativity and associativity when you're talking about operators. Okay. Yeah, further uses of gradients. So there is something called derivative of gradients, okay, DOG operator, and then there is this LOG operator, which is Laplacian of the Gaussian. So these are. There is also the derivative of Gaussian. What am I saying? Did I say? Sorry. This is derivative of Gaussian. I think I said something wrong. And this is the Laplacian of Gaussian. Okay. So this is the first derivative, second derivative. And these are again used to, so you want to use the Laplacian, but suppose there is a lot of noise in the image. Okay. Then that noise is going to create too many fake edges. Okay. So then, or fake, how do you say it? So in the moon image that I showed earlier, okay, you see all these dots in between. Okay. Now here, of course, for the moon image, it's not noise; those are craters. But in some other image, this could be noise. Okay, and then you can see all these things will be created in the Laplacian. So if this actually corresponds to noise in the image and you want to reduce its effect on the Laplacian, what you do is first you blur the image and then take the Laplacian. So that process is called Laplacian of Gaussian operator. And this again can be explained as a convolution because essentially, so D2 means I'm taking the Laplacian, okay, and G means the Gaussian. So if I take the Gaussian of the function of the image and I want to take its Laplacian, you can think, first of all, you can think of applying the Laplacian as a convolution, right? This is what we saw earlier. So doing this is same as doing this. And by associativity, it is same as doing this first and then doing this. Okay. So this is like taking the Laplacian of the Gaussian and then convolving with the image. Okay. So this is an operator in itself. Okay. And then one can write this. So also one should remember that the Gaussian, the derivative of a Gaussian is a Gaussian. And the second derivative of a Gaussian will also be a Gaussian. You will have some different constant in the front. Okay. So essentially in DOG as well as in LOG, the net result is that the kernel of this will again look like the Gaussian kernel, okay, although the weights will be different. But the properties will be the same like the Gaussian, like separability properties and no directional bias and those kind of properties are here as well as in the DOG operation. Yeah, but the point is that it can be viewed as convolving F with some kernel.